Did you know that a small piece of a certain material, about the size of a marshmallow, can glow red-hot all by itself for decades? It's not magic, it's science. We're talking about plutonium-238, a remarkable substance that has become the lifeblood of our most ambitious journeys into the cosmos. This material is a special type, or isotope, of plutonium that isn't used for weapons. Instead, it acts like a tiny, incredibly long-lasting furnace. It naturally gives off a steady stream of heat as it decays, and, well, this heat can be turned into electricity to power spacecraft where sunlight is too faint to be useful. It is the warm, beating heart that keeps our robotic explorers alive in the cold, dark depths of space. Imagine you're sending a robot to Jupiter, or even farther, to the icy plains of Pluto. Solar panels, which work so well for satellites orbiting Earth, become almost useless out there. The sun is just a distant, dim star. This is where plutonium-238, or Pu-238 for short, comes to the rescue. By harnessing its natural radioactive decay, scientists and engineers have created power sources called radioisotope thermoelectric generators, or RTGs. These are essentially nuclear batteries that can provide reliable electricity for many, many years without any moving parts or maintenance. This constant power allows our robotic emissaries to operate their instruments, communicate with Earth, and survive the extreme temperatures of deep space. This incredible power source is made possible by the fundamental physics of atoms. Pu-238 atoms are unstable, and over time, they break down, releasing energy in the form of alpha particles. These particles are not very penetrating. A simple sheet of paper can stop them, but they carry a lot of energy. When a chunk of Pu-238 is assembled, these countless tiny decays add up to produce a significant amount of heat. The material literally glows with its own internal warmth. It's this dependable long-term heat that engineers have cleverly converted into the electrical power that has fueled some of humanity's greatest voyages of discovery, pushing the boundaries of what we know about our solar system. So, while the word plutonium might make you think of something dangerous and destructive, it's important to remember that science is all about understanding and harnessing the properties of matter for different purposes. In the case of Pu-238, we have taken an element with a notorious reputation and found a way to use a specific version of it for something truly inspiring: the peaceful exploration of the universe. It's a perfect example of how scientific knowledge allows us to turn what might seem like a scary concept into a tool for progress and discovery, letting us reach for the stars and uncover the secrets they hold. The story of plutonium begins back in 1941, at the University of California, Berkeley. A team of brilliant scientists led by Glenn Seaborg was experimenting with the building blocks of the universe. By bombarding a heavy element called uranium with subatomic particles, they created something brand new, an element that didn't exist in nature. They named it plutonium, after the then planet Pluto, continuing the celestial naming theme that followed uranium and neptunium. This discovery was a monumental achievement in chemistry and physics, opening a new chapter in our understanding of the atom and the immense energy locked inside it. At first, the focus was on a different isotope of this new element, plutonium-239. This version, Pu-239, has a very different set of properties. It can sustain a powerful, explosive chain reaction, releasing an enormous amount of energy all at once. This destructive potential was recognized during World War II, and Pu-239 became a key component in the development of nuclear weapons. The atomic bomb used in the attack on Nagasaki in 1945 was powered by Pu-239, forever linking the name plutonium with immense power and devastation in the public mind. This historical context is important for understanding why the word can be so alarming. However, science rarely has just one application. As our ambitions turned toward the stars in the space race of the 1960s, NASA faced a major challenge: how to power missions that would travel far from the sun. Scientists knew about the other isotope, Pu-238. Unlike its weapons-grade cousin, Pu-238 does not sustain a chain reaction. Instead, it decays steadily and predictably, releasing heat. It's like the difference between a firecracker and a slow-burning log in a fireplace. One is a sudden, violent explosion, while the other provides a gentle, long-lasting warmth. This made Pu-238 the perfect candidate for a space-based power source. This crucial difference is what separates the two tails of plutonium. While one isotope changed the nature of warfare, the other quietly revolutionized space exploration. The first satellite to use a Pu-238 power source, Transit 4A, was launched in 1961. Since then, it has become the go-to energy solution for our most daring deep space missions. This dual identity of plutonium, one for destruction, one for discovery, is a powerful reminder that the application of scientific knowledge is a choice. We can use our understanding of the universe to build weapons, or we can use it to build spacecraft that expand our horizons and inspire generations. The incredible journey of making plutonium-238 begins with a material that many might consider nuclear waste. The starting ingredient is an element called neptunium-237. This substance is an actinide, part of the same family of heavy elements as uranium and plutonium. It is produced as a byproduct in nuclear reactors that generate electricity. For a long time, neptunium-237 was simply stored away as radioactive waste, a challenging material to manage with no obvious purpose. But scientists, in their quest for a perfect space power source, saw an opportunity to transform this leftover material into something extraordinarily valuable for exploring the cosmos. The process starts when this neptunium is carefully retrieved from its storage. It is typically transported as a stable chemical solution from facilities that reprocess spent nuclear fuel to a specialized laboratory, like the famous Oak Ridge National Laboratory in the United States. Safety is the #1 priority at every step. The neptunium solution is moved in robust, shielded containers designed to withstand extreme conditions, ensuring that none of the radioactive material can escape into the environment. This meticulous handling is crucial because, even in its initial state, neptunium is highly radioactive and must be managed with extreme care by trained professionals. Once the neptunium solution arrives at the lab, the first major step is to change its physical form. A liquid is difficult to work with in the precise stages that follow, so it must be converted into a solid. Through a series of chemical processes, the neptunium is precipitated out of the solution and treated until it becomes a stable, manageable powder. This powder is much easier to measure, handle, and shape for the next phase of its transformation. This conversion process is performed in controlled environments, often within glove boxes, which are sealed containers that allow technicians to manipulate the materials safely using heavy-duty gloves. This initial stage sets the foundation for everything that follows. It's a remarkable example of scientific alchemy, taking a byproduct that was once considered waste and beginning the process of turning it into a high-tech fuel source. The careful preparation of the neptunium powder is essential for ensuring the quality and consistency of the final plutonium product. Every batch is meticulously tracked and analyzed to make sure it meets the strict specifications required for creating a power source that will one day travel millions, or even billions, of miles from Earth. It's a story of recycling on an atomic scale. After the neptunium has been converted into a fine, solid powder, the next step is to give it a specific uniform shape. This isn't just for looks. The shape and density of the material are critical for the next stage of the process. The neptunium powder is carefully measured and poured into a die, which is a specialized mold. Then, an immense amount of pressure is applied, squeezing the powder together with great force. This powerful press compacts the loose powder into small, dense, cylindrical pellets. Each pellet is made to be almost identical in size and weight, a bit smaller than a dime. Uniformity is key here. During the next phase, these pellets will be exposed to a flow of subatomic particles, and it's vital that this exposure is as even as possible for every bit of neptunium. If the pellets were lumpy or had different densities, some parts might get more exposure than others, leading to an inefficient and unpredictable transformation. To prevent this, each and every pellet undergoes a strict quality control check. This is done using non-invasive techniques, like taking precise measurements and sometimes even using X-rays to look inside the pellet for any hidden cracks or imperfections. This pressing process is a delicate balance of force and precision. Too little pressure, and the pellet will be too fragile and might crumble. Too much pressure, and it could crack or become too dense, which might affect the later chemical separation steps. The engineers and technicians have perfected this process over decades of experience, learning exactly how to create the ideal neptunium target pellets. It's a bit like making a perfect ceramic, where the consistency of the clay and the pressure used to shape it determine the quality of the final product. Every pellet must be perfect for the mission ahead. Once a batch of pellets has been pressed and has passed the rigorous inspection process, they are ready for the most dramatic part of their journey. They are carefully loaded into aluminum tubes, which are then sealed. These tubes containing the neptunium pellets are now called targets. They are the bullseyes that will be placed into the heart of a nuclear reactor. This careful preparation ensures that the neptunium is securely contained and positioned perfectly for its transformation into plutonium. The humble gray pellets are now on the verge of becoming something much more powerful. This is where the real nuclear magic happens. The sealed tubes containing the neptunium pellets are transported to a special kind of nuclear reactor, one designed to produce a very intense flow of neutrons. Neutrons are one of the basic particles that make up the nucleus of an atom. The targets are carefully placed inside the reactor core, where they are bombarded by a constant, powerful stream of these neutrons. This process is called irradiation. It's kind of like putting the pellets in a special kind of oven, but instead of heat, this oven cooks the material with a storm of subatomic particles. Inside the reactor, an amazing transformation takes place at the atomic level. When a neutron strikes the nucleus of a neptunium-237 atom, it can be absorbed. This absorption makes the neptunium nucleus unstable and heavier, briefly turning it into neptunium-238. However, this new form is very short-lived. In just a couple of days, the neptunium-238 undergoes a natural radioactive process called beta decay. It emits a tiny particle, and in doing so, one of its neutrons transforms into a proton. This change in the number of protons fundamentally changes the element. The atom is no longer neptunium, it has become plutonium-238. This irradiation process is incredibly complex and must be managed with extreme precision. The pellets have to stay inside the reactor for a specific amount of time, often for many months, to allow enough of the neptunium to be converted into plutonium. However, they can't be left in for too long. If a newly formed Pu-238 atom gets hit by another neutron, it can change into a heavier, less useful isotope. The goal is to maximize the amount of Pu-238 while minimizing these unwanted side reactions. All of this happens inside heavily shielded chambers, called hot cells, where robotic arms handle the intensely radioactive materials to keep human operators safe. After their long bath in neutrons, the targets are removed from the reactor. They are now far more radioactive than when they went in, containing a mixture of leftover neptunium, newly created plutonium, and other fission byproducts. The pellets, which went in as simple neptunium, now hold the precious material that will one day power a mission to another world. The next challenge is to separate the tiny amount of valuable Pu-238 from everything else in the mixture. The alchemical cooking is complete, but now the delicate work of purification must begin. Once the irradiation process is complete, the target pellets are a hot radioactive mix of different elements. The main goal now is to isolate the newly created plutonium-238, which makes up only a small fraction of the material inside the pellets. This is a highly complex chemical separation process that must be carried out remotely in shielded hot cells. First, the irradiated pellets are dissolved. The aluminum cladding that held the neptunium is dissolved using a solution of sodium hydroxide. Then, strong nitric acid is used to dissolve the remaining material, creating a radioactive liquid cocktail containing both neptunium and plutonium oxides. The next step is to separate the plutonium from the unreacted neptunium and other impurities. This is achieved using a sophisticated technique called ion exchange chromatography. The acidic solution is slowly passed through tall columns filled with a special material called an ion exchange resin. This resin is designed to attract and hold on to certain elements more strongly than others. As the solution flows through, the plutonium sticks to the resin, while most of the neptunium and other contaminants pass right through. This is a highly efficient process, capable of capturing over 95% of the plutonium from the solution. After the neptunium has been washed away, a different chemical solution is used to release the plutonium from the resin. What comes out is a solution containing highly purified plutonium. When this liquid is processed further to turn it back into a solid, it forms a remarkable substance, a bright purple powder of plutonium oxide. This colorful powder is the prize that scientists have been working so hard to obtain. The leftover neptunium isn't discarded. It can be recovered, converted back into pellets, and placed back into the reactor to create even more plutonium in the future, making the process highly efficient. The purification stage is a testament to the precision of modern chemistry. It involves separating atoms of one element from another with incredible accuracy, all while dealing with materials that are intensely radioactive. The final plutonium oxide powder must be exceptionally pure, often close to 90% Pu-238, to be suitable for use in a space power system. Any impurities could affect its performance and long-term stability. This beautiful but dangerous purple powder is now ready for the final steps, being pressed into fuel pellets and sealed for its journey into space. With the highly purified plutonium oxide powder now ready, the final manufacturing stage begins. The goal is to create the actual fuel pellets that will be loaded into the space-bound power generator. Just like with the initial neptunium pellets, the plutonium powder is carefully weighed and pressed into a cylindrical shape under high pressure. These final pellets are designed to be dense, strong, and stable. After being pressed, they are subjected to an intense heating process known as sintering. The pellets are placed in a special furnace and heated to a very high temperature in a sealed environment. This heating process is crucial for increasing the density and strength of the pellets, turning them into a hard, ceramic-like material. A denser pellet means more Pu-238 is packed into a smaller volume, which leads to a more efficient heat source. The sintering process also makes the pellets incredibly durable, which is essential for withstanding the harsh conditions of a rocket launch and the long journey through space. Each finished pellet of plutonium-238 oxide is a small powerhouse. A single pellet, weighing around 150 grams, can generate approximately 84 watts of thermal energy, glowing red hot from its own radioactive decay. But before these pellets can be used, they must be safely contained. Each pellet is encapsulated in a small, incredibly tough container made of a special iridium alloy. This metal is chosen for its extreme strength and its ability to withstand incredibly high temperatures, even higher than the melting point of the plutonium fuel itself. This encapsulation provides the first layer of safety. This small container, called a fuel clad, is then sealed shut by precise welding, creating a permanent, protected home for the plutonium pellet. This ensures that the radioactive material remains safely locked away. Finally, each encapsulated fuel source undergoes a battery of brutal tests to ensure it is virtually indestructible. The capsules are subjected to intense vibration tests that simulate the violent shaking of a rocket launch. They are smashed with high-velocity projectiles, exposed to extreme heat, and crushed under immense pressure to simulate any possible accident scenario. High-resolution X-rays are used to inspect the welds and ensure there are no internal flaws. Only the fuel sources that pass every single one of these grueling tests are certified for flight. This obsessive focus on safety ensures that the plutonium poses no risk, even in the unlikely event of a launch failure. The legacy of plutonium-238 is written across the solar system, etched in the data sent back by some of humanity's most iconic exploratory missions. Over 25 missions since the 1960s have relied on the steady, reliable power of RTGs. One of the most famous early uses was during the Apollo missions to the Moon. While the main spacecraft ran on other power sources, the scientific experiment packages left behind on the lunar surface by the astronauts were powered by Pu-238. This allowed them to continue collecting and transmitting valuable data about the Moon's environment for years after the astronauts had returned home. Perhaps the most legendary explorers powered by plutonium are the twin Voyager 1 and 2 spacecraft, launched in 1977. These incredible machines conducted a grand tour of the outer solar system, giving us our first close-up views of Jupiter, Saturn, Uranus, and Neptune. Solar panels would have been completely useless on this journey. Thanks to their 3 RTGs, the Voyager probes are still operating today, more than 4 decades later, as they travel through interstellar space. The vast emptiness between the stars. They are the most distant human-made objects, still faithfully sending back data from beyond our solar system, all thanks to their plutonium hearts. More recently, Pu-238 has enabled us to explore worlds in incredible detail, The Cassini probe, which orbited Saturn for 13 years, was powered by RTGs. This long-term power source allowed Cassini to study the planet, its magnificent rings, and its fascinating moons, including Titan, with its thick atmosphere, and Enceladus with its hidden ocean. On the surface of Mars, the Curiosity and Perseverance rovers use a more advanced version of the RTG. This power system not only provides electricity for their instruments day and night, but also uses the excess heat to keep the rover's electronics warm enough to survive the frigid Martian nights. These missions, and many others like the New Horizons probe that flew past Pluto, simply would not have been possible without Plutonium-238. It is the key that has unlocked the outer solar system for us. It allows us to send robotic explorers to places where the sun is too weak, the temperatures are too cold, and the missions last for decades. Each of these journeys has rewritten our textbooks and transformed our understanding of the universe. The silent, steady glow of plutonium has illuminated the darkest and most distant corners of our cosmic neighborhood. As we look to the future of space exploration, our ambitions are growing larger. Scientists dream of sending orbiters to the ice giants Uranus and Neptune, launching missions to explore the intriguing moons of Jupiter and Saturn, and perhaps even sending probes to other star systems. All of these grand voyages into the deep dark corners of the cosmos share one critical need: a reliable, long-lasting, and powerful source of energy. For the foreseeable future, Plutonium-238 remains the only technology capable of meeting this demand. It is, quite simply, an irreplaceable tool for deep space exploration. However, there is a significant challenge. The production of Pu-238 is an incredibly complex, time-consuming, and expensive process. For many years, the United States stopped producing it altogether, relying on a stockpile that was slowly dwindling as it was used for missions like Curiosity and Perseverance. Recognizing the impending shortage, NASA and the Department of Energy have worked to restart production, but the current output is very small, only a few kilograms per year. This limited supply creates a bottleneck, forcing mission planners to make difficult choices about which ambitious future projects can move forward. The need for more Pu-238 is becoming urgent. A future flagship mission, like an orbiter designed to study Neptune and its moon Triton, would require a much larger quantity of plutonium than is currently being produced annually. To make these kinds of bold missions a reality, production capacity must be significantly increased. This requires sustained investment in the specialized facilities and the highly skilled workforce needed to handle these materials safely and efficiently. International cooperation could also play a role, pooling resources and knowledge to ensure that humanity has the power it needs to continue exploring. Ultimately, the quest to produce more Plutonium-238 is about more than just manufacturing a specific material. It's about our commitment to continuing the journey of discovery. It's about whether we will have the tools to answer fundamental questions about our universe, such as whether life exists on the ocean moons of Jupiter or Saturn. Every pellet of Pu-238 we create is a key that can unlock a new world. By investing in this incredible technology, we are investing in a future where humanity continues to push boundaries, to venture into the unknown, and to reach for the stars.